Okay, so we were talking about data sets for deep learning. So let us talk about some of the available data sets. Okay. So first of all, we'll see for NLP, right? So for NLP, what are the type of data sets that we have? So if you go to this website, it gives you a whole lot of data sets which are available, and you can use them for any work that you want. So people basically use benchmark data sets because they've already been used by others for some algorithms, and they have results available for them. So if you have a method where which you have discovered, you can try it out on that, and you can see um, whether you are getting better results. Okay, and you can compare it with methods, algorithms which are already existing basically. Okay, so let first we'll look at the image data sets which are available. Okay, we have what is called the Kaggle challenge website, which contains image and speech data sets. And one of the very popular data sets is what is called the ImageNet. Okay, so this ImageNet has 14 million labeled images, okay, scanning more than 2000 categories, and each image will be of one class like balloon or strawberry, etc. Okay. So these are um, the images which we have got from the ImageNet data set. So you can see that they are images of one particular object mostly, right? This is a house, this is a bird, these are dogs, etc. Okay. Next is the what is called the MNIST data set. So MNIST data set is a data set of handwritten digits. So you have handwritten digits 0, 1, 2 up to 9. Okay. So 10 classes are there basically. Class 0, class 1, class 2, etc. And you have a training set of 60,000 examples and a test set of 10,000 examples. It's actually a subset of a larger set. Okay. So we just use, most people just use this particular data set which is available, and you find that the digits have been already normalized and centered. So why is this actually required? Okay, so you may find that when you take these handwritten digits, there may be variations in it. Okay, for example, if we take if we consider a box like this, okay, or say the image is going to be in this. So how you find it is you have pixel information here, okay, and then you have pixel information for the next row, etc., and those are going to be concatenated to form the pattern, right? Now you may have 1 0 which is like this, right, and you may have another 0 which is like this, say, right. So you find that there may be variations both lengthwise, breadthwise, rotation, in all sorts of ways. So what you need to do is you need to actually normalize your data set so that all of them are in the same way, right. So you will find that this particular digit will be expanded to fill this whole thing, right. And if you find that it is rotated on one side, that will be also changed, etc. So what you are going to do is you are going to center it and you are going to size normalize it so that it can be used properly. So this data set has all these things already done for you. Then another data set is for what is called the CIFAR 10 data set. Okay, so this consists of small images. Okay, the resolution of these images is not very good, but you find that it's possible to distinguish one image from another image. Okay, so each image is 32 into 32 pixels with 10 classes. Okay, and there are 60,000 images for each of the 10 classes, right? So what are the classes you have? You have things like airplanes, cars, birds, cats, deer, dogs, frogs, horses, ships and trucks, right? So this gives you your CIFAR data set. So you find single things like a horse, a bird, automobile, truck, etc. So what you can see is resolution is not so great, but it's possible to differentiate from one image of one class to images of another class basically. Then you have what is called the COCO data set, Common Objects in Context. So these are actually images in which the segmentation has been provided. So you can actually check out if you're carrying out some type of segmentation, you can see how well your segmentation is behaving also. So you can see here, if you see this image, each of these has been segmented. Similarly here, the people have been segmented, etc. So everything, some segmentation has been done to help in checking out how well your segmentation is basically doing. And then we have the visual question answering data set, which consists of images like this, right? So you have 265,016 images, right? And for each image you have at least 3 questions. Okay, for example, things like who is wearing glasses? Okay, here is the man who's wearing glasses, here is the woman, where is the child sitting, etc. Right? And then you have at least 3 questions with 5.4, okay, 5.4 questions on average it says per image. So at least 3 questions and 10 ground truth answers per question, right? 3 plausible answers per question. And then you have of course evaluation metric to check whether whatever answer you are getting is right or wrong basically. So those are all the image data sets. Next we will talk about the natural language processing data sets. Okay. Another popular data set is what is called the IMDb data set, which is called the movie data set. So it has reviews of different movies. So it has 25,000 movie reviews for training, 25,000 movie reviews for testing, and these reviews you have to check whether they are positive or negative. Okay, is the movie good or is the movie bad, right? So that is binary sentiment classification. Okay, are you happy with the movie or are you not happy with the movie? Okay, is it plus or minus, +1, -1, whatever, right? Next is what is called the 20 news group data set. So this contains information about news groups. So you have 20,000 messages from 20 news groups. Okay. So by news groups, like I said, it could mean that is it from politics, is it from entertainment, etc. Then you have the sentiment 140 data set, again used for sentiment analysis. So you have tweets. So what are tweets? Tweets basically have a maximum of 140 characters. Okay, so it will be may not be good proper sentences also. Okay, so the way people tweet and it has 6 features, namely polarity, ID of the tweet, date of the tweet, the query, username of the tweet and text of the tweet, right. So you can use all these to carry out sentiment analysis basically. Then you have WordNet. So WordNet is a large data set of English synsets. So synset is a group of synonyms which describe a concept. So you have 117,000 synsets, and this is a very useful tool for any NLP problems that you are going to use. Then we have the Wikipedia corpus, which consists of 1.9 billion words from so many articles, right. So this is also used for some NLP problems basically. Next we come to the speech data sets. So you have the TIMT, that is a speech transcription data set. Okay, so you have 630 speakers with American and English dialects basically, okay, which you could use for transcription. Then you have Vox Celeb, which consists of 1000 celebrities voice transcription. Okay, so what you do is you try to find out whose speech is it, okay. So these are those, and these are actually language translation data sets, WMT, right, 15 and 14, where you have English Czech language, English German language data sets. And this has 15.4 million sentence pairs. Okay, so you are given the English sentence and you are given the corresponding Czech sentence, and then you can check how your translation is working using that. And this has 4.5 million sentence pairs. Then you have English Vietnamese language translation data set. Then you have speech recognition data set with multiple speakers, right. So speaker recognition is one thing that you could work on. Then this is for visual speech recognition, has hundreds of hours of TED Talk videos, right. So these are all the speech data sets which are basically available, which can be used for tasks. Okay, now what we need to see is that when we come to deep learning algorithms, you have the data sets. For example, you may have your input in the form of a sentence, right. Now, how do you convert that sentence so that it can be input into your data learning algorithm? So what you are going to do is you are converting it into a vector in this way, right. So what is it that you do so that you can convert the sentence into a vector of say real numbers which you can feed into your deep learning algorithm. So that is what we are going to see over here, because this is very crucial, because otherwise how do we work on the natural language processing, right. If it is images, it's fine, you can feed the pixel information and that pixel information can represent your image. But how do you, and in the case of speech also, you have a waveform and you can feed that waveform into the deep learning algorithm. But in the form of, for the case of NLP, how do you do? Okay, so that is what we will see next basically. Okay. So what you need to do is you need to turn your text into a vector or an array, okay, which will consist of either integer values, real values or Boolean values, okay. So it could be just zeros and ones, or it could be have real values, or it could have integer values, okay. You can also use what is called a one-hot encoding. Okay, so for example, if you have only a few words which you need to represent, suppose I have 4 words, okay, say 1, 2, 3, 4, which I need to represent. What I can do is I can have a binary string of 4 bits, right? And you can use what is called a one-hot encoding. So the one-hot encoding is that one of the 4 elements will be 1, the others will be 0. Okay, so suppose I want to represent 1, I can represent it by the one-hot encoding in this way. If I want to represent 2, I can represent it by the one-hot encoding in this way. So all the words that you have, so many elements you will have, and one of the elements, if you want to represent, you can represent it as a one-hot encoding basically. Another one is what is called the bag of words. Okay, so suppose you have a number of words which you need to represent together. You can look at it as a bag of words where each word will also have the frequency. In other words, how many times does it occur? Okay. For example, like they say dog may occur 4 times, okay, etc. So that type of representation is called the bag of words basically. Then you have what are known as the word embeddings. Okay, so word embeddings are vector representation of words learned from the context training. Okay, so how do we? So we can. It's something like the coordinates of the words, right? So there are a number of techniques for this. One is called the word to vec, okay, in which there are 2 types of techniques: continuous bag of words and the skipgram. And then you have the global vectors or the glove. So glove embeddings. You have what is called the fast text embeddings, etc. So these are different embeddings which can be used. So basically, word to vec is very popular, and recently the glove embeddings are also very popular. Okay, and you can see that the words which are represented by these vectors, if you take words which are sort of similar to each other, you will find that their vectors are close to each other basically. So if you use say principal component analysis to bring down the dimension, okay, so if you have something like a d-dimensional vector, if you bring it down to say 2 dimensions, and if you represent it or if you plot it, you will find that words which are similar are close to each other. Okay, so for example, you can see here word embeddings which have been used here for different words. So 2 documents have been used, document X, document Y. Gave a research talk in Boston is one of them, had a science lecture in Seattle. So you can see that when these 2 are taken and you find the word embeddings, and then you do the dimensionality reduction to two dimensions, and when you plot these, you find that gave and had are somewhat close to each other. Science and research are close to each other. Talk and lecture are close to each other, etc. Which shows that there is some meaning in taking these word embeddings. So the word embeddings are properly representing the words that we are basically talking about. So here we have again another example taken. So there are 4 words: dog, puppy, cat and houses, and these are the embeddings, the word embeddings. So you find that we have taken 7 vectors, okay, which together represent the various words that we have taken. And then you are using principal component analysis to carry out dimensionality reduction, and we are reducing it to 2 dimensions. So these are this is the plot of these 4 words. So you find that dog and puppy are somewhat close to each other, dog and cat are somewhat close to each other, whereas houses is little far away from them, etc. And similarly, if you take man, woman, king and queen, you find that king and queen are here and woman and man are here, okay, which shows that some meaning can be extracted from this basically. Okay, another important thing which is done is what is called the batch normalization. So whenever the data which you are going to feed into one of the layers, okay. So suppose we take a batch, okay. So now that batch may be having values which are very high, there may be values which are low, etc. So some type of normalization helps in getting better results. So generally what do you do if the input is from layer H, you find the mean of all that input. Okay, so suppose the input you have is Hi, right? You'd find the mean and the standard deviation of that, and then you can find the Hi normalized value, which will be Hi minus mu divided by sigma plus epsilon. Okay, sigma is a standard deviation, where epsilon is a smoothing factor, and then you can find the value of Hi which you are putting into the next layer to be equal to alpha into Hi normal plus beta, where alpha and beta are some learnable parameters which you are going to basically use. So using batch normalization helps you to get better results, because you may find that the data which you are feeding into a layer, some values may be very high, some values may be very low. So it will give more importance to the values which are high than to the values which are low. So if you carry out something like batch normalization, you can reduce all the values to values between 0 and 1, okay, making them somewhat closer to each other. Okay, so here we talk about the deep neural network. So this is exactly like the neural network, the multi-layer perceptron we saw. You have the input layer, hidden layer 1, hidden layer 2. So you increase it, so you have more number of hidden layers, okay, till you get the output layer. So this could be the deep neural network which we talk about. But what is the disadvantage here? We can see that the complexity becomes very high because the number of links that we have between nodes is extremely high, right? We can see how much complexity there is, and it may be difficult to use this type of a network basically. So it will be good if we can learn a small model. And all the edges that we have here, do we really need all of them? Okay, you may not really need all of them. Can some of these be shared? Okay, so if can you combine them together in some way, basically. Okay, so this is your deep neural network, and we convert that into what is called the convolutional neural network. So convolution neural network arranges its neurons in 3 dimensions, right? You have width, you have height, and you have depth, right? So if you look at this face, okay, this shows you your original image, right? And this original image basically you have it in a number of layers, so that is what gives the depth. Okay, so you may have say 3 layers here. So the 3 layers may correspond to the red, green and blue channels, okay, or it could correspond to some filters which you are using, etc. Okay, so what you get is you get, and in each layer you will get a 3-dimensional layer in this way. Okay, so that is a very higher level view of what is going on in the convolution neural network basically. So what is it that you do in the CNN. Okay, so first of all you have an input here, and this input you carry out convolution on this input. So you are converting it into convolutions, and by using what are called filters, and depending on the number of filters you will have the number of layers of convolution here. Okay. So what you are doing basically here is you are extracting the features, okay, and then you are carrying out what is called pooling. So pooling actually reduces the size of this convolution layer and makes it in a smaller one. And once you do convolution and pooling, finally you carry out the fully connected layer here. So the fully connected layer is exactly like what you did in the multi-layer perceptron. So this could consist of either one layer or you could have another layer also, and it carries out the classification here. Okay, so what happens here is you are extracting the features, and the higher level features will be available in this fully connected layer, and you are carrying out classification of those features which you have here. So this is the CNN architecture basically. So let us look at the layers that you have. First of all, we have the convolution layer. So this is the first layer which is used to extract various features from the input. Okay, so you have a filter of size m by m. Okay, and you are taking this filter and you are superimposing it on the input layer. Okay, and you are sliding the filter, and as you slide the filter, you are finding the dot product between the filter and part of the input image of size m into m, and this information will go into the next layer. Okay, and you get what is called the feature map basically. So that's what happens in the convolution layer. Then next we get the pooling layer. Okay, the convolution layer is followed by a pooling layer. So in the pooling layer, basically you are taking a window of some particular size and you are reducing that value to a smaller value. Okay, so basically you are decreasing the size of your layer. Okay, so there are many ways of doing this. In max pooling, you take the largest element, and then in the average pooling you take the average element, or you can take the total sum basically. So these are the various ways that you can do. And finally we have the fully connected layer, which consists of the weights and biases. So in the fully connected layer, it consists of the final after you do convolution and pooling a number of times, you take the final output which comes and you flatten it. Okay, and the flattened vector goes through the fully connected layers to give your classification output. And then you have what is called the dropout. So what is this dropout? The fully connected layer will be really large, okay, and working with such a large size can lead to overfitting. So what do? You have a dropout layer. So about 30% of the nodes are dropped out, okay, and you work only with the other 70% of the nodes basically. Then you have the activation function, exactly like the activation function which we used in the neural networks, right? So that gives you a function between what you get, you pass it through the either ReLU function, softmax, tanh, or a sigmoid function, and each of these functions have a specific usage of that. For example, this is what is called the ReLU function. So you find that depending on the value of x that you have, you get different values of y, right? So the value of y is an integer which depends on the value of x, and you find that if it is minus, then your output will be 0 basically. And softmax function, you have different values of xi and all the input values probabilities sum to 1. So what you are getting as a softmax of xi will be a probability of that is the output which you are using. Okay, so we will continue in the next session on the rest of the convolution neural network.